There are many different aspects of automotive testing, ranging from the measurements themselves, how you connect with the infotainment system, and more complex testing needs such as voice assistance readiness and pre-qualification. Firstly, I'm going to talk about the measurements themselves, things like frequency response, max SPL, and buzz, squeak, and rattle. And then we'll make some in-car measurements so that you can see how easy it is. Next, we'll look at various connection methods that infotainment engineers have to contend with, like open loop testing, Bluetooth connections, and the A2B bus. And finally, we'll take a look at some of the other audio measurements that you can make using SoundCheck. For example, active noise cancellation and voice assistance readiness. Let's start with the measurements. I've been part of a working group on in-car acoustic measurements, working under the AES Technical Committee on Automotive Audio. Over the past couple of years, we've been working on trying to develop recommendations for some of the important audio measurements that need to be made in cars, specifically frequency response, max SPL, and impulsive distortion, which is sometimes called rub and buzz or squeak and rattle if you're from the automotive world. I'll give you a quick explanation of what those measurements are, then show you how we can make those measurements in SoundCheck. Frequency response is a common audio industry measurement. We use it all the time for speakers, headphones, any device that plays sound. It's a quantitative measure of the sound pressure level as a function of frequency, and it gives a clear visual indication of the spectral balance in the car. One of the things we are looking out for here is a smooth and gently sloping frequency response, usually with more bass than treble. We want to make sure that there are no sudden peaks or dips in the curve that would indicate that certain frequencies are being emphasized or attenuated with respect to the rest of the spectrum. Max SPL is important because consumers want to compare how loud different infotainment systems can play inside a car. The maximum SPL, or max SPL, is the maximum sound pressure level that a car's infotainment system can reproduce and sustain inside its cabin with all its windows, sunroof, convertible top, etc. closed. This measurement combines all the components of the system, including speakers, amplifiers, power supply, etc. There are two methods that are recommended: overall max SPL and max SPL spectrum, regardless of total harmonic distortion. It is very difficult to characterize distortion in a modern-day infotainment system because all the signal processing, which was not designed to play back sine waves, and it's also difficult to correlate with subjective listening perception. Impulsive distortion measurements give us a way of quantifying unwanted distortion artifacts, such as buzzing panels, rattling cables, loose particles, and air leak noise in a car. These are important to identify as they are easily discernible by the passengers, giving the perception of poor quality. These may be either parts defects, for example, the speaker itself, the enclosure, or the subassembly. Or it may be introduced by the mounting, for example. Plastic clips or even the panel themselves might be excited by high cone excursions, creating a buzzing sound. So next, I'm going to demonstrate how we make these measurements in a real car, using SoundCheck, of course. We'll make all three of the measurements I mentioned earlier. Fortunately for us, they all use the same test setup, which makes it really easy to measure all three characteristics together at the end of a production line. So let me talk you through the setup for these tests. Now, the physical setup that I'm using is based on the recommendations from the AES Automotive Audio Technical Committee that I mentioned earlier. Obviously, if you want to compare measurements between cars, it's critical to use the same measurement conditions, so there is value in the whole industry standardizing. If you're just doing it for your own in-house evaluation, it's also important that you are consistent, but you can, of course, determine your own setup. Anyway, for the purpose of this demo, I'm going to use the AES Technical Committee's proposed configuration as a guideline. All right, let's make some measurements. We use a 6-microphone array to represent the driver's head in the driver's seat. This is pretty standard for automotive audio test. Let's get this set up. First, I'm going to put the mics into the array. I'm using our own SEM measurement mics, the short version, because they are nice and compact, but you could use any 1/4-inch measurement microphone. Now I'm going to attach this array to the tripod so that we can adjust the height to the position where the driver's head would be. Now I'll connect all the cables. Now let's look at the positioning in the car. I am positioning the tripod legs as far back as I can get them on the seat, right against the backrest. The height and angle of the seat are set to the minimum or lowest position. Now the AES is working on defining some very specific dimensions between the pedal and backrest and the height of the stand. 105 centimeters from the brake pedal to the backrest in a straight line, and a microphone array height of 72 centimeters from the seat to the 2nd and 5th microphones. That's the 2 middle ones. It also specifies the incline of the backrest, so it is 10 centimeters from the 3rd and 6th microphones. For the purpose of this demo, it doesn't really need to be that precise, but as you can see, I'm making sure that I have recorded the dimensions I am using, and the mic array is in a fairly typical driver head position. The front passenger seat should be in about the same position as the driver's seat. There we go. That should do it. Now let's connect our audio interface. I'm going to use our AmpConnect 621, which is a 6-in, 2-out audio interface. You can use any audio interface that works with your microphones and offers the resolution and other characteristics needed for reliable and repeatable audio measurements. This one is particularly good for automotive tests because it has 6 input channels which match up with the 6 mics. And all channels offer mic power. It's also TEDS compatible, so if you happen to have TEDS microphones, you can save yourself some setup and calibration time. Now let's plug the microphones in. And I'm going to connect this up to my computer using the USB cable. Now, as we'll demonstrate later, there are many ways that your audio measurement system can be connected to the car infotainment system. SoundCheck can connect to the car using a USB drive, the car's Bluetooth, or even with the A2B bus. Here I'm going to use Bluetooth because it is fast, convenient, I don't have to get in and out of the car, and most importantly, I don't have to worry about damaging my hearing when measuring max SPL. I've got a BTC 4149 Bluetooth interface. This enables me to send test signals via Bluetooth. I have this all plugged in and turned on, and now I'm going to pair it with the head unit. I'm going to add it here under my Bluetooth devices, Add Device, and Start Search. You can see it shows up as a Bluetooth device, so I can add it. And we're all set to go. Now the last part of our setup is checking that the head unit's audio mixer settings are in the default position for a standard and repeatable configuration. So we go to the settings panel. First, we're going to make sure we have flat tone controls, so make sure all of these are set to the middle position. We want to make sure the balance is in the middle, which it is. That's the default setting. We also want to be able to use different sources, for example, Bluetooth, USB memory stick, and so forth. Although I'll be doing this measurement using Bluetooth, it's good to have other options for comparison. Now the important part, particularly for the max SPL test, we need to crank the volume all the way up to 11, as they say in Spinal Tap. I didn't realize until I came to demonstrate it that the sound on this car does go all the way up to 11. So if anyone from Tesla is watching this, nice job. So now we've done that, we're ready to go. Now let's get testing. For the actual measurements, I'm going to use our SoundCheck test system. Over the past couple of years, we've introduced several new features that are really useful for automotive testing. For example, the multi-channel RTA. Anyway, let's jump straight into some measurements. Okay, so I'm going to demonstrate the 3 different in-car measurements I mentioned at the beginning: frequency response, maximum sound pressure level, and impulsive distortion. We'll start with frequency response. We're going to measure this at 80 dBA SPL. This measures the frequency response of the infotainment system at a nominal listening level. Then I'm going to run max SPL. That's with the volume turned all the way up to the maximum. I'm going to show this as a spectrum and an overall C-weighted sound pressure level, which is only appropriate when measuring extremely high sound pressure levels. Lastly, I will show impulsive distortion, where we want to look for buzz, squeak, and rattle. Okay, let's start with the frequency response. The Bluetooth interface is paired to the head unit, and the pink noise is played out of the loudspeakers. The reference excitation signal is a monophonic, full-scale pink noise signal with an RMS level of -12 dB FS, as defined in the AES-17 standard. I'm just going to hit start. You'll see the RTA come up, and you can hear pink noise being played. You can see the output of the 6 microarray with each individual microphone, plus the black line, which is the power average of all 6 microphones. You can see on the multimeter that it's at 80 dBA. This is the main listening level proposed by the AES Technical Committee, and additional measurements are also recommended by increasing or decreasing the listening level in steps of 5 to 10 dBA from this value. And here you can see the frequency response curve. It is pretty smooth with a significant amount of bass and some treble boost. Now let's measure max SPL. We'll use the same broadband monophonic pink noise that we used for the frequency response, but this time we'll crank the volume up to 11, and even outside the car, this is going to be loud. That's loud. Yep, that's loud. If you do this a lot, you might want to use hearing protection. It's hitting 110.5 dB, and we're going to play it for 30 seconds and take the linear average or LEQ. Here you can see the reading on the 6 microphones and the black line representing the spatial power average. And now you can see that it calculates the overall max SPL as 111 dB C-weighted. Also, we have the max SPL spectrum from 20 Hz to 20 kHz, and the curve shape has not really changed much from our previous frequency response curve measured at 80 dBA. Lastly, I'm going to make an impulsive distortion measurement. Here we're looking for buzz, squeak, and rattle due to interior vibrations caused by the loudspeakers mounted in different locations in the car. We're using a high to low swept sine wave at 80 dBA. That's pretty loud too. Okay, here's the results. What we're looking for is some spikes in the loose particle envelope curve on the bottom right, and some bumps in the perceptual rub and buzz curve on the bottom left. You can see no bumps in the perceptual rub and buzz curve, and just mostly background noise in the loose particle envelope. Now I'm going to introduce a piece of plastic in the left door pocket to represent a loose component that will vibrate. Hopefully we'll get to hear and see the difference when this rattles. Let's make that measurement again, but at a higher level. You can see there is some rattling going on in the loose particle envelope and some rub and buzz going on just below 200 Hz near resonance. We have a reading of about 45 fons on the perceptual rub and buzz measurement. Any PRB above 20 fons is quite audible. So you can see it's one simple setup, and you can make all these measurements very quickly. This same setup is appropriate for a whole range of end-of-line tests, both in the R&D lab and on the factory production line. So the next thing I want to cover is connectivity. Cars are complex systems, and most offer several ways of connecting audio to the head unit to play test signals out of the infotainment system. I just did all my demos using Bluetooth because this was the simplest and most convenient option for this type of car. You can also put test signals on a memory stick and play them via the head unit, or even access the car's infotainment system via the A2B bus. One of the neat things that we offer with SoundCheck is the option to interface via any method you choose, and also to run open loop tests which automatically compensate for the time delays when playing back signals, for example, from a USB drive. We're now going to review these three common connectivity methods: Bluetooth, USB drive, and A2B. We'll demonstrate how they work and discuss the pros and cons of each. Firstly, Bluetooth. Let me first address one of the questions I am often asked. Is Bluetooth accurate enough? The answer to that is yes. Absolutely, provided that you are using a high-quality, calibrated Bluetooth interface rather than an inexpensive Bluetooth dongle. This allows you to control the codec selection, for example, aptX for wideband frequency response and bit depth. Now I'm going to hand over to my colleague, Steve Tatarunas, who will explain more about testing via Bluetooth and demonstrate some measurements.
Thanks, Steve. Most commonly, consumers use their Bluetooth-enabled devices to connect to the in-car infotainment system for delivery of music and voice communications. But other applications allow for management of vehicle diagnostics, vehicle access, personalization of controls, and even vehicle sharing. Bluetooth connectivity gives us a standardized method to connect to the car's audio system to both send and receive audio test signals, simplifying what might otherwise be a complex hardware and wiring setup. Earlier, you saw Steve Temme perform a variety of in-vehicle measurements, all of which were made over a Bluetooth connection between SoundCheck and the car audio system. The Bluetooth signals were transmitted using the BTC4149 Bluetooth interface from our measurement partner Portland Tool & Die. Unlike Bluetooth dongles, which are essentially black boxes having unknown characteristics, the BTC4149 is a laboratory-grade Bluetooth 3.0 compliant RF interface. It supports a comprehensive suite of codecs, protocols, and other significant settings and can be configured through touchscreen controls, a command line interface, or message steps in a SoundCheck sequence. These options provide unparalleled control over protocol selection, pairing options, and transmission power. I'm often asked if using Bluetooth is accurate enough for automotive testing. There's one thing you should bear in mind. You should not use an unqualified Bluetooth dongle. Only a laboratory-grade instrument such as the BTC4149 will give you the accuracy and control that you need. Configuring the BTC4149 is simple. When SoundCheck detects the presence of a BTC, it will automatically configure SoundCheck's hardware and calibration with the appropriate digital signal channels and signal paths. Once this configuration is in place, we can then use message steps in a SoundCheck sequence to configure, pair, and disconnect the BTC from the device under test. Let's take a look at how we can use message steps in a SoundCheck sequence to configure our BTC4149 to establish a Bluetooth connection and send a test signal to the audio system. Since we're in the studio today and don't have a car available, I'll be connecting to this car kit as opposed to a car's head unit. Okay, so now it's time for a quick demo in SoundCheck, and what I hope to show you here today is how we're going to be using message steps to configure the BTC and discover available devices and open up the audio channel between the BTC and the device so we can continue on with our acquisition and analysis in SoundCheck. So as you can see here in the sequence editor, I have three message steps called BTC Setup, BTC Get Address, and BTC Connect Audio. And I'll be using those to send commands to the BTC while the sequence is running. So let's quickly open these up and take a look at the functions of these steps. So BTC setup is for the codec selection, and it allows us to select the A2DP codec. In this case, we'll be using SBC, and we can also select the HFP codec. I'm not going to be using HFP in this demo, but these are the available options for the HFP codec. The next step, BTC get address, is where the BTC will go out and look for discoverable devices. So this is a device connection step. And there are connection options here where we can connect by name, connect by address, or disconnect. And the other user configurable parameter here is the inquiry time or the discovery time. How many seconds do you want to spend searching the local area for a discoverable Bluetooth device? Pretty good value here is 10 seconds. And then lastly, we have the actual connection step where we open up the audio stream between the BTC and the connected device. What is most important here is the audio channel selection, whether or not we're going to connect over A2DP or HFP. And in this case, we'll be doing an A2DP connection. So otherwise, the sequence is pretty straightforward SoundCheck sequence. We're going to be using virtual instrument acquisition, similar to what Steve was showing in his previous demos. We'll be using signal generators and RTAs, and then a display step and a couple of operator dialogues to start and finish the sequence that give the operator some options about connectivity. So let's run the sequence. So the first step in the sequence is a message step, and it asks the operator if they're currently paired with the device under test, which we're not. So we're going to say no, and we'll go through the pairing routine. We're searching for discoverable devices, and there's a couple that have showed up here as available, and I know from experience that I actually want this C68 device here. So once I click OK, we'll proceed to the next message step where we're going to connect to the audio, and the sequence will progress from there. And so here's our final display, and there's one last message step asking me if I want to disconnect from the DUT, and I have the option of keeping the connection open in case I want to make another measurement here, or if I'm done, I can disconnect. So I'm going to say yes. And we're left with our final display, and what we're actually looking at here is the response of the car kit sending the signal over to an FM tuner, and then we're sending the tuner's response back into SoundCheck. So that's why we don't have a very flat response here. We're really seeing the characteristics of the tuner here in the final response. So there's a quick demo of how to use message steps in a SoundCheck sequence to connect to your Bluetooth device, send audio, and disconnect. Using SoundCheck in a device like the BTC4149 makes connecting to a vehicle's infotainment system a simple process. Back to you, Steve.
Next, I'm going to cover USB drives. This is the simplest option if you only need to make occasional measurements or your car does not have an auxiliary input, as it avoids the need to configure and calibrate a Bluetooth interface. However, it's not without its drawbacks. You need to record the stimulus with a long period of silence at the beginning to enable you to plug it in, hit play, and exit the car before you are deafened with extremely loud pink noise in your ears. It's not ideal, but if you have no other way or only need to make measurements infrequently, it works. The reason that this is even an option is because SoundCheck offers some sophisticated open-loop measurement capabilities. If you think about it, when you're making any measurement that requires the stimulus and response signals to be aligned, for example, phase response or time delays, you need to be able to trigger the recording when the test signal starts playing and account for the inconsistent time delays. In SoundCheck, we offer several different techniques for triggering a recording and automatically detecting the time delay in the measurement. And if you want to learn more, there's plenty of information about open-loop measurements on our website. Anyway, that's open loop testing in a car using USB drives. The other situation we encounter with automotive testing is the A to B bus. This often comes into play more when you are testing car microphone arrays rather than speakers, as you need to capture the signal via the car's internal microphones rather than your own measurement microphones. Most modern cars contain microphone arrays for everything from voice control to active noise cancellation. I mentioned earlier that SoundCheck is great at getting signals into and out of any device, and this is no exception. SoundCheck can communicate directly with the A2B bus to enable you to make all the same measurements that you would with a conventional wired setup. I'm now going to hand over to Mark Latshaw, who will demonstrate how we can measure MEMS microphones via an A2B interface.
Hey, my name is Mark, and I'll be demonstrating an A2B application for automotive testing. A2B is a high bandwidth bidirectional digital audio bus. A2B is capable of transporting data, control information, clock, and power using a single 2-wire, unshielded twisted pair cable. In an automotive application, this can be used with microphones for voice recognition, communications, or active noise cancellation, including road noise cancellation. There are some major benefits of using A2B. Multiple devices can be daisy-chained together. A2B also supplies power to all devices in the chain, so local power supplies aren't needed. Since only a single twisted pair cable is required, the total weight and complexity of the system can be much lower. In contrast, traditional wiring would require multiple connections, power supplies, which all use heavy copper wire. With lighter vehicles and higher fuel economy, these are all important design considerations. In this example, I'm using an Analog Devices A2B sound card. This sound card is connected to an 802425 eval board. This eval board has TRS line in and line out, so I have 2 line ins and 2 line outs available. I'm then connected to 2 boards over here, each of them with 2 PDM MEMS microphones. So in total, I have 4 MEMS microphone inputs, 2 line inputs, and 2 line outputs. We're also connected over here via USB to my computer. Using an Analog Devices program, Sigma Studio, I can set up the configuration for these devices. I'm also using an Audio Connect and an SC amp connected to a speaker over here so I can play out pink noise to test these microphones. Now we'll take a look at Sigma Studio by Analog Devices. So in this software, we can set the configuration to match what our actual hardware is. So I have my sound card configured, it's connected to the 802425, and then I can select which channels are available. So again, on this setup, I'll have 4 microphone inputs, 2 line inputs, and then 2 line outputs. This will be dependent on the configuration of your specific setup. If your hardware is different, you'll need to set it in Sigma Studio to match what you're using. Now that it's configured, we can set it to the device, make sure that it matches the settings, and what I've done in this is using ASIO streams for my audio channels. So we'll take a look now in SoundCheck. If we go into Setup Hardware, we'll be able to see that I now have 6 ASIO inputs and 2 ASIO outputs, which are using the Analog Devices A2B sound card. I also have my 2 inputs and outputs for my Audio Connect. In Setup Calibration, we'll open up the table, and you can see for the input side, I've created 4 input signal paths that are all tied to the microphone. So inputs 1 through 4 will correlate to the MEMS mics 1 through 4 on these boards over here. And on the output side, my source speaker is configured to play out of my Audio Connect, out of this speaker here. So we'll save this, and now if I run the sequence, it will play signal out and record in on my 4 microphones. Great, so as you could see there, we had an RTA with 4 discrete input channels. We were reading the 4 microphones on my setup over there, and we're able to put these into memory, set limits on them, and test them whenever we want, further in a SoundCheck sequence. Once the data is captured via A2B, we can test it the same as if it was from any other source. For example, if these microphones are going to be used for noise cancellation, we could then write a sequence for that specific use case.
So as we come to the end of the seminar, I just want to mention some of the other things SoundCheck can be used for. We've focused here on basic in-car measurements, but SoundCheck is extremely powerful and flexible and can actually be used for virtually any audio measurement inside or outside the car. For example, within the car, it can make virtually any audio measurement, such as measuring internal and external noises, such as road and wind noise, for active noise cancellation quantification. It can also carry out a wide range of tests on in-car voice assistants, such as Google Art and Apple CarPlay, as well as proprietary voice assistants and hands-free communication systems. Outside the car, it can be used for laboratory measurements of virtually any component, speakers, microphones, communications, etc., at the design stage. In fact, we even have many specific options for communication measurements such as polka, double talk, and other industry standards.